again. In this example, you will learn how to assemble a flexibility matrix and use it to solve for unknown redundant forces. We're being asked to use the flexibility approach to find the reactions of this particular beam. First thing we want to do is check the determinacy, and we will go ahead and neglect the axial motion on this. And so I want to identify the reactions that I have associated with this. So I have R1, M1, R2, R3, and M3. So if I count that up, that will then give me 5 unknown forces. I haven't made any cuts, so the number of structural pieces I have is 1. That means that the total number of equilibrium equations which I have available to me is 2. Remember that if I'm neglecting axial, I do not have access to the sum of forces in the x equation. I only have access to the sum of forces in the y and the sum of moments, and that's why I only have 2 equations of equilibrium there. Indeed, the problem statement actually tells me that I can choose the moments at 1 and 3, so that's this and this, and the reaction at 2 as my redundants. Then I'm going to need to go ahead and apply the flexibility approach to identify those 3 reactions. Now let's understand why the problem statement was asking us to do that. Because we have 5 unknowns, 2 equilibrium equations, and that results in me being statically indeterminate to the 3rd degree. What this means for me is that I need to remove those 3 redundant forces. And as I do that, I come up with this particular beam. Now before we bother doing any calculations, it would be wise for us to get a consistent set of units, so I'm going to come back here and just indicate that 2 kips per linear foot is equal to 1/6 kip per inch. My beam lengths here, at being 20 feet, I can rewrite those as being 240 inches, and this one being 180 inches. This will make sure that all my calculations that I do will have a consistent set of units of kips and inches. Now back to the primary structure. This is where we ended up removing our redundant forces, all 3 of those. And I'm going to go ahead and sketch the deflected shape here. And I want to label quantities of interest to me. So here is theta 1. Here is delta 2. And theta 3. So you'll notice that what I'm doing is I'm looking for the deformation at the locations where the redundants had been. Now redundant structure number 1 says that I will go ahead and add on that redundant moment. I will get a deflected shape associated with this, and then I will go ahead and look at the deformation of each of those locations. So the rotation at 1 due to the moment at 1 is equal to the flexibility coefficient 1, 1 due to the moment at 1. Look at this here. This is the deflection at 2 due to the moment at 1 is equal to the flexibility coefficient times that applied moment. And then the rotation at 3 due to the moment at 1 is equal to the flexibility coefficient times the moment at 1. I need to go ahead and do the same type of process here where I apply the redundant force, R2, and I apply this redundant moment, M3, and I'll go ahead and sketch their deflected shapes and their respective displacement. So take a close look at the subscripts and recall that the first subscript is the location where the deformation is occurring, the second subscript is the location where the force is being applied. And that is why we actually notice that that is all due to that, and this term is all due to that. And we can use these sketches to go ahead and generate our compatibility equation. And the way we do that is we go ahead and sum up the rotations at each of these locations. So that's what we'll do here. We'll get theta 1 plus F11 M1 plus F12 M2 plus F13 M3. And we know that the real rotation at that location is going to be 0 due to the original support condition. Now we will go ahead and write those summation equations for each of the other two locations, and then rewrite it in matrix formation. So recognizing once again that we have the displacements and rotations that come on our primary structure, and then we have these flexibility coefficients that are denoted with the lowercase f, and we have our unknown redundant forces M1, R2, and M3. So with just a little bit of algebraic rework and moving the theta 1, delta 2, theta 3 to the other side, we can write it in this matrix form. Now remember what our end goal is we are trying to solve for what these unknown redundant forces are. That means I need to be able to compute the displacements and rotations on my primary structure, and then I also need to find these flexibility coefficients. And those flexibility coefficients are identified from these flexibility structures, and they look very, very similar to our redundant structures, other than they have unit moments and unit forces that are applied at the redundant locations. Okay, so we get these deflected shapes, something like this, and we can begin to label what these look like. So this would be F11. So it's the rotation at 1 due to a moment at 1. And more explicitly, the way we ought to read this is it is the displacement at 2 due to a unit moment at 1. Displacement at 3 due to a unit moment at 1. And so in short, what we recognize is that when we calculate flexibility coefficients, it's nothing more than calculating deflections at certain locations. Now because these beams are simply supported, it becomes very easy then to use beam charts to compute our desired quantities. So let's come back here to the primary structure, and let's recognize that we're trying to find theta 1, delta 2, and theta 3 subjected to that kind of a load. So we'll go to this beam chart, and we recognize here's our equations for theta and displacement. We will then note here that the W that we were using is that 1/6 kips per inch, and that the length that we will be using is 420 inches. Remember, that is the entire length of that primary structure as we come back here. It's that 180 plus the 240. So we will also be interested in knowing what the deflection is out here at this location, which is at a distance of x equals 180 inches. Okay, so you'll notice that we've got this theta 1 going on, and you'll see what kind of rotation we get for that. We will see the delta 2 going on, and that's being evaluated at that 180 inches, as we previously indicated, and the resulting deflection. And then we will also acknowledge that the rotation at point 3, which incidentally on the beam chart is being labeled 2, it is going to be simply the opposite sign of what we had over to the far left. Now what we're going to need to do is solve for the flexibility coefficients. The flexibility coefficients require us to come in and place these unit moments. So just look at this beam chart. I'm going to need to place a unit moment right here at this location. We're once again going to have that length being 420 inches. And so since I am applying a moment in the opposite direction of what the beam chart says, we will notice that a negative is placed in there. And then I simply go through the separate locations and identify what the values are associated with that using the information up here. Let me take an opportunity to point out the units on this. Look at this. So what that is that's the rotation at that location due to a unit moment. Displacement at that location due to a unit moment. We can do very similar things for the other two locations. Remember what we're doing is we are now applying a unit load coming up this way. And so you can see then the respective quantities that we will get coming out of that. And then we've also got the situation where we will apply a unit moment here and we can get the respective quantities coming out of that. What you have to become accustomed to is if you're going to use beam charts is when the load is not showing up where the beam chart shows, you're going to need to mirror the response quantities that you get. What you should have also noticed is that in this case I solved for 3. In this case I only solved for 2, and in this case I only solved for 1. Not because there weren't 3 quantities I needed here, but because we know that anytime I have 2 different subscripts, so F32, I know that that is the same as F23. That's using Maxwell's theorem of reciprocity. So what I can do then is I can take all my known displacements from the primary structure, I can drop them into my matrix formulation. Here are all my flexibility coefficients, and this represents the unknown redundant forces that I'm trying to solve for. So doing some matrix math, I take the flexibility matrix to the other side by taking its inverse, pre-multiplying there, and I will then get the following quantities. So this is 350 kip inches, 35.7 kips, negative 875 kip inches. So that found my redundant forces. Then what I can do is I can transfer those over here. So 35.7, 350 kip inches, 875 kip inches, and then I can go ahead and solve for my other forces, R1 and R3. And I can do that using the equilibrium equations that I have below. It may be helpful for you to remember that I have a total resultant force here of 70 kips, and that would be a moment arm of 210 inches. So you'll see that in the respective equilibrium equations that we've got running, and we can then solve for these values. And that concludes this example. Remember that it's always a beautiful day for studying structures.